Hello. Okay, so last time we had proven 3 theorems about integration. We had proven, let's see here, this approximation for integration using this length function. So the integral over a path is bounded by the length of the path multiplied by whatever bound we can put on the integrand. So this was useful. We had some other little notes about reversing the orientation of a contour and concatenating 2 paths and their relationship to integration. We sort of stated these without proof. Maybe we'll put them in an appendix. We also had, so sort of our important theorems that we got through are if we have a differentiable function over a convex domain, then its integral over a triangular loop vanishes. That was the proof that we had done all through this section here. The second proof that we had done is slightly more general than that, which is if we have a differentiable function on a convex domain, again, same premises, then the integral of a function f over a closed loop in S vanishes. So this is sort of the second theorem. So the first one is for triangular loops, the second one is for general loops, just overall. We left the polygonal loops as unproven. It could be proven using the triangular case in an induction. Essentially, you would just cut the loop to reduce the number of vertices until you get a triangle. Into 2 different segments. Yes, but essentially, this was our proof. So our proof was approximate the paths using this polygonal approximation, so you just sort of connect the dots between these points. And as the number of points you use increases, the polygonal path approximates the path really well. Between streams, I fleshed out this proof a little bit more. It's essentially the same idea. What we had done originally was essentially, so we just sort of observe that this whole path, the polygonal path, at least point-wise, converges to the original path sigma. That's sort of straightforward. But we went a little deeper editing when we were doing some edits. So originally we had just said, well, if you just take this projection of this polygonal approximation, you just end up with the polygonal approximation of the projection. And so since these polygonal approximations have these properties for complex paths, we just sort of said, well, by this property, if they have this property for these paths, then just using that same property on each projection sort of extends to the total path. We fleshed that out a little more. We included an explicit proof for the real case. So actually this paragraph here, we just sort of explicitly went through the steps of justifying that. So if we take, for example, if our path sigma is real, if it always takes real values, this projection, that's a typo, that should be underscore subscript. This projection, p sub 1 of sigma t, well, of course, as a contour, by definition, all of the projections have to be piecewise continuous. But since sigma, the path sigma in this case is only real valued, let me see, there we go. Since the path in this case is only real valued, then it is equal to its first projection. In fact, this is the same if it's complex. And so we just deal with this real value case first. So the polygonal path is just composed of secant lines. A secant line is just it's just sort of the line connecting 2 points on the curve. But for mean value theorem, the secant line has a slope, which is somewhere on the part of the curve that it is secant between. So the derivative of this polygonal approximation, at any given point, this derivative is somewhere in the image of the derivative of the original derivative of sigma. So since this, basically the derivative of a polygonal path is just a piecewise constant, and all of those constants will be one of the values that sigma prime takes. This image, sigma prime, it's continuously differentiable, so it has to be bounded. And since all these sigma prime, these for sigma sub n, these derivatives, these polygonal paths, are subset to that image, they're subset to this bounded set. So all of these sigma prime sub n of t, these are bounded across all n and t. And also, so that's the first part, is they're bounded, and then we have to show pointwise convergence, but for real paths that's also really easy. Since sigma prime is continuous at all but finitely many points, and the secant lines have a slope which is somewhere within their x range, then eventually at any one of these points the derivative will, of this polygonal path will approach just sigma prime of t. So the polygonal path approaches the curve that it is approximating both in its derivative and also pointwise, while being bounded. Actually, the derivative is being bounded as well, which is much more important in this context. For the general case, we just do the projections. So we just sort of do this little observation that if we take the projection of the polygonal path, it's the polygonal path for the projection of the original curve. So if we have this curve being real on each projection, then each one of these will have that property. They will converge pointwise. Their derivatives will converge pointwise and be bounded. Since this curve is bounded on each projection and converges pointwise on each projection, then it converges and it's bounded. So that sort of gives us this thing. Ultimately, the complex case, so this is for real. The complex case is essentially exactly the same thing. You just, instead of using the p sub k projections, you would use the real part and imaginary part operators. But otherwise, it's exactly the same sort of song and dance. The ultimate goal of this is that we prove that these sigma sub n prime of t is bounded across all n and all t, and converges pointwise to sigma prime of t. We had already proven, since f is continuous and sigma n converges pointwise, this f of sigma n of t converges pointwise to f of sigma t. And this whole section here proves that this sigma sub n prime of t converges pointwise and is bounded, converging to sigma prime of t. And then we just apply dominated convergence. So each of these paths here, or rather we can say the integral of f along this path sigma is equal to, so we use the substitution rule to get this, by dominated convergence, this is just equal to the limit of these integrals for these polygonal paths. And each of these polygonal paths is just 0, because we have path independence over polygonal paths from the triangular case, which is the previous proof. So that was sort of how we had worked that out. The next proof that we want to do is right here. So I edited the wording of how we're going to prove this. So originally it was if it's simply connected, and we have a differentiable function, then it vanishes on closed loops. But the proof actually is a little more general than that. So actually what we've done, we've said our theorem statement is let S, the domain, be locally convex, as always, and let f be a function on S which is differentiable. And then we're going to say, suppose we have two contours, sigma and gamma, which are homotopic. So we'll get into that in a second if you're not super familiar with homotopy. But they're homotopic curves, which means they can be continuously deformed into one another. If we have these two contours, which are homotopic, then the statement of the theorem is asserting the integrals of f over either these paths, sigma or gamma, are identical. So this is sort of our statement. So if we have two paths and we can continuously deform one into the other, then the integral is the same. Something that's important, so I'll state the definition of homotopy here first so that we can see what we're looking at. So we'll have, since sigma, gamma are homotopic, we have a function f which maps the interval 0, 1 squared to a, or sorry, we should actually say homotopic in S. We should specify that. That's important. Okay, so we have this function, so we're actually not going to map it to A, we're going to map it to S, which is a subset of A. So, since these curves are homotopic, we have this, actually not just any function, a continuous function f mapping the unit square to the domain S, such that f of t0 equals sigma t, and f of t1 equals gamma t for all t in 0 to 1. So essentially, what this is asserting, this just having this homotopy, is we have a, essentially, we can think of f as a function, so f is sort of as a function of t and s. And so we can think of s is sort of like our time. T is our position on, I know we've sort of got them reversed to how normally you would think of t. But if s is our time, and t is our, maps our position on the curve, for each value of s, f of t, as a function of t, will just be a curve. It'll just be some path. Not necessarily, oh, actually there's one more restriction. Yes, yeah. So this is sort of how homotopy captures the idea of continuously deforming a loop. There's one key point actually that I've missed, which is, so we do have the first, so when s is 0, when time is 0, the first curve is sigma, and when time gets up to its maximum, the curve is gamma. But also, it needs to be such that the endpoints are fixed. And also, so we have f of 0s is sigma 0, which is also gamma 0. And f of 1s is sigma 1, which is gamma 1 for all s in 0, 1. So this is the second condition. So the first condition for these two conditions, this is saying the first curve at time 0 is sigma, and at the end of time we have the gamma curve. So we have a continuous deformation of curves from sigma to gamma. The second condition is saying that in addition to the fact that we're sort of continuously deforming these curves from sigma to gamma, we want the endpoints to always be fixed in place. So at the beginning of each curve, regardless of s, every beginning of the curve is always sigma 0, which is also gamma 0. And at the end of every curve, the endpoint of each curve, regardless of time s, the endpoint of each curve is the same, which is sigma 1, which is equal to gamma 1. So these are sort of the conditions on homotopy. These are going to be really useful for us. Yes. So so the way that we're going to maybe something that's important to note actually is that it is not required for this proof. It is not required for each of these, for each, fixed value of s. It's not required for this f of t. It's not required for that to actually be considered a contour. Our restrictions on contour is that each projection is piecewise continuously differentiable, or that it is the antiderivative of a piecewise continuous function. It's actually not necessary to fit that condition at all points in time s. It is only necessary for it to be satisfied at the endpoints. So the first curve has to be contour, and the last curve has to be a contour. But in the middle, it can just be any path. And so we'll have to sort of the proof actually allows us to have a lot of freedom in that regard. That comes from the fact that S is locally convex. We'll see how that plays in. So let's see. So how do we want to start out? So we have this continuous function f. So it has its conditions. So what we're going to do is we want to say, so we want to start out by saying, we want to produce an a finite open cover of convex sets. That's what we'll do. So, so since 0, 1 squared is compact and f is continuous, the image f of this whole unit square, so the total image of f, all the points that f takes, is a compact set. So then we can say, actually we'll be a little, yes, okay, yeah. So since S is locally convex, then for each point, actually let's do it this way. We'll say let U subset to the power set of S. Be the set of all relatively open convex sets, subsets of S. Since S is locally convex, this U is an open cover. So open cover just means that it's only open sets, and every point in S is in at least one of those sets. So then we can say, since 0, 1, the unit square is compact and f is continuous, the image f over 0, 1 squared is a compact set. So we have, since U is an open cover with this compact set, we can say there exists a finite subcover, and we'll call this U sub f, I guess, capital F, which is subset equal to U. So this is the definition of compact set, is every open cover has a finite subcover. So we have this finite set U sub f, which is it's a finite subset of this capital U. Also, if you want f to be stand for finite or for the function f, doesn't matter. Yes, so since U is open and it's an open cover of this compact set, so this image actually, in fact, is a subset to S, because f is a homotopy in S. So it's a subset of S, which is compact set, and we have this open cover, so we have this finite subcover. So that means that there are finitely many open convex sets in this U sub f, and every point in the image of f is contained in one of these open sets, in one of these compact sets. So that's sort of our first step. Actually, I think maybe we don't need this condition. We'll leave that there for now. So the next step is we want to cut up the domain of this square into tiny subsquares, and we want them to cut them small enough so that every square is contained within some convex set. So some convex open set. So we'll say for each n in natural, consider a partition of 0 1 squared into n by n subsquares. We will show that there exists some n such that every subsquare has its image under F as being subset to one of the convex open sets in U. I think actually we don't need the full use of F. We'll check. Maybe we might. So that's sort of our intention. So we're gonna partition the square into n by n subsquares and show that there is some n such that every subsquare has its image as being subset to one of these convex open sets. So to do this, let's see. We'll say, let me think. We want to do, yeah, okay, so let's say, convenience, for each n and for each capital N, and we'll say, oh gosh, n and ij, actually we'll do jk in 0 to capital N. We don't want to actually 1 to capital N. Let h sub jk capital N be equal to the set, actually the image, F over the set of, let me think. To j minus 1 to j times to k. Okay, let's see how that looks on paper. Okay, so so for each n and jk, so we're sort of using these coordinates, jk as coordinates. So we're cutting up our square into n by n subsquares. These n by n subsquares are essentially just these squares. Yes. And so h is the image of our function f over, so h, we're using the jk subsquare with partition size n. So h sub jk with n is the image of f under the jk subsquare, using the partition size n. That's what we have. And so we're going to say, and so specifically these are the closed subsquares. So technically this isn't a partition because we're including the edges for every square, but that's fine. So we're going to say let, for each n and jk, let h be this. And we'll say, by contradiction, suppose that for every n, or rather, suppose that there does not exist some n such that for every jk there is an open set in U with h sub jkn subset to O. So by contradiction, we're going to say, assume that no matter how big we make n, we can't make these squares small enough to be subset to one of our convex neighborhoods. So it follows that for every n and jk, or sorry, for every n, there is some j sub n and k sub n such that for every, let's see, for every open set O, open convex set in O in U, there is a point x sub n comma U actually we can say how does this go? Let me think on this. Okay, such that every oh yeah, let's actually be more like vague, such that there is no O in U having h sub j sub n, k sub n, and n subset to O. So what we're going to do is actually just find a limit point. So, this, since we can say each of, actually let's change our coordinates a little bit to make this a little easier on us. We'll do a 0 indexed. Okay, so since each point, so we'll have j over n, k over n is in this unit square 0, 1. Which is sequentially compact, there must be a limit point for Okay, there we go. So what we want to say is, we're going to cut this up into a partition, and we're saying by contradiction, suppose we can't cut it up fine enough so that each one of these little squares, these subsquares, the image of the subsquare, so that each one of these subsquares is subset to a single convex neighborhood. So suppose this is impossible, that we can't put each subsquare subset to one of these neighborhoods. It follows that for every n, there is some specific jn and kn, such that no open set has this property. No open set covers that particular tile. So for every n, there has to be some tile which can't be covered by one single open set, one single convex open set. Since each of these points, so j over n and k over n, since actually this should be j sub n over n. Since each of these points is in this unit square, which is a compact set, then we should have a limit point for these terms are approaching this point t comma s. Now we can just say, actually we'll say, let's do, there must be a, let's do a conversion subsequence, we'll be a little more specific. A lot of indices here. Okay, so we have this conversion subsequence of these points. We can maybe cut these into tiles to be a little more explicit, but I think this is okay. So we'll edit it a little later when we finish writing the proof. So there's this conversion subsequence however, since S is locally convex, there is O in U with F of ST in U. And moreover, we can say let's see, what do we want to say? We want to be clear about this. So essentially, we want to say that find this limit point on this domain, and then put its image of this limit point in a neighborhood. Sorry, this should be O, not U. Find a neighborhood, a complex neighborhood for this point. What we want to show is that eventually all of these neighborhoods are actually subset to this specific O. If we take, so let's say if we take any, let's say XY in this tile. Yeah, actually let's do that. Okay, so we're gonna do a little more. So we're gonna cut up this unit square into explicit tiles. I don't want to type this over and over again. This little chunk here. So we're gonna say we're gonna let H, instead of H being the image, we'll just do H is just this subtile by contradiction, so there's blah blah blah, such that, and we'll just do F of H. So H is the subtile and F of H is its image. Follows that for every n, there is some of these having F of, and so on. So since each of these points is in 0, 1, which is sequentially compact, there must be a convergent subsequence, so on and so forth, with all of these points arranged to ST. Since S is locally convex, there's an O in U with f of st in O. And moreover, if we take any, we'll just say x sub m, actually, for any sequence of, let's say, x sub m, y sub m in this tile h sub, we have j sub n sub m and k sub n sub m and n sub m. We must have x sub m and y sub m going to this point s comma t. So and since O is open, there is some point m0 after which x sub m0 and y sub m0 is in O. So we're saying no matter what sequence we take out of these, so where are we here? So we're saying, so each of these little coordinates, j sub n over n, k sub n over n, each of these coordinates is in this unit square. So this is actually the, we can think of this as the bottom left corner of the subtile H. So each of these bottom left corners are in the 0, 1. This is sequentially compact, so there's a convergent subsequence. Since S is locally convex, there is an open set, a convex open set O and U, which these f of st in O. So this limit point, this f of st is in S. S is locally convex, so we just find this convex neighborhood for this point in S, in capital S. Any sequence of xm and ym which are in these squares will have this limit, xm ym goes to st. And since O is open and f is continuous, we have f of x sub m, y sub m going to f of st, which is in O. So there is some point after which xm and ym are in O for all sufficiently large. So we can do this, since we're doing this by contradiction, we can actually construct this sequence. So we're saying each n, let this be that. Contradiction suppose there's not this, so that f is subset O. Every n there is j sub k such that there's no O in U having this subset to this. Each of these is sequentially compact, and must be convergent subsequence. S is locally convex. We do have an open set, and so we can say double subscript. I'll fix that in a second. Convergent subsequence is this open set, and by construction we must be able to find a point. We'll say x sub m, y sub m, which is in this tile h sub jk n, for which f of x sub m, y sub m is not in O. However, we must have, so we have this limit So we must have xm, ym going to st, and since O is open and f is continuous, since f is continuous, we have f of xm, ym going to f of st, which is an O, and but O is open. And that is roughly the first part of the proof. So to recap, we're saying take this unit square, cut it up into subsquares, and suppose by contradiction that there isn't a sufficiently fine grid such that every one of these subtiles has its image on F as being subset to a single convex open neighborhood. If this is the case, then for every n there's j sub n k sub n such that no O has this subset relation. We can probably cut out this sort of contradiction, so, this double negation. So by contradiction, suppose that for every n there's some j sub n k sub n. There we go. Yeah. So for every n there's j sub n k sub n such that no O in U, so no convex open neighborhood O in U has this subset relation, so has the image of this specific tile. So for every n there's a tile which can be put subset to this open set. Since each of these corner points are in 0, 1, which is sequentially compact, we find a convergent subsequence. S is locally convex, so we find this O with f of st in O. And we can find xm and ym. Xm, ym, which is not in O. Hold on. Orange subsequence, O, and we can find this. And, we can find xm, ym in this tile. This should be having parentheses. Yes, so we find x and y in this tile, for which f of xm, ym is not in this open set. So all of these tiles were selected. Each of these tiles at each time n, for each partition size n, was selected so that no open convex set in U covers it. But since we have this, these subsequences, so for each one of these things, we just find x and y, which is not in O. Because that was by premise. None of these tiles can be covered by any of the convex open sets. So none of them can be covered by O. But since these tiles, all of these tiles are sort of converging just to this single point, since one of their points converges, in fact their corner point tends to this point, and their diameter tends to 0. These are just real tiles in R squared. Since all of these tiles tend to this single point, this subsequence in particular has to tend to this point. Since f is continuous, we have f of xy. This is tending to f of st, but this is in this open set. So we have to have some x. We have to have some m. We have to have some m. So if we have this limit to an open set, eventually these points have to be staying inside this open set. So there's no way to approach a point in an open set from outside of the open set. So there's a contradiction. So let's say, let's clean this up a bit. So for each n, let this be that by contradiction. Suppose that for every n, blah, 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 and so on. Okay, so by the above, we have found n such that for all jk, there is some O in U with H sub jkn subset to O. And actually we'll call this O sub jk. Okay, nice. So that's the first half. So the first half is finding our partition that does this. And then the next half is actually about integration itself. It's a lot easier. So let's clean up also this. This first paragraph. So actually we didn't need that other premise. Okay, so we've constructed all these. So by construction we found n such that for all jk there's some O with this tile hjkn subset to O. So now we can say let's see, how do we want to do this? So we want to use these squares. So yes, we want to use these squares to show that these integrals are 0. So by the previous theorem, it follows that let's see. So this previous theorem states explicitly the integral of f over closed loop minus vanishes. So we can say for each, let me think. So we want to start by cutting up the sigma curve. So follows that for each jk, we have, we'll say, the integral of across sigma from, let's think, of f of x, our function dx. This is just the sum from, we'll do something, some lower bound to something else, I think n minus 1. Do j is the x, so j equals 0 to n minus 1 of the integral from some lower bound to some upper bound, f of x dx, and these lower upper bounds will be sigma of something to sigma of something else, and these will be j over n to j plus 1 over n. Okay, so, oops. So by the previous theorem, the integral of f over within, or sorry, any integral of f over a path in any O sub jk, so any of these convex open sets, is path independent, since f is differentiable and O sub jk is convex. That's what we want. Yes, so O sub jk is convex. So we're saying, where are we? Down here. By the above, we have, so we have n, all these open sets. By the previous theorem, any integral of f over a path in any O sub jk is path independent, since f is differentiable and ojk is convex. So for each jk, we have this integral. So if we integrate across sigma of this f of x dx, this is the same as just summing up these integrals. So essentially we go from sigma 0 to 1 over n, and then from 1 over n to 2 over n, and so on and so forth. The reason each of these works is because essentially we know that sigma is just, we can just form sigma by concatenating a bunch of paths that sort of plot out these points and follow the path sigma, but it's path independent. So we can say, actually, let me double, no, this is fine, okay. Which follows, since sigma of t for t in j over n to j plus 1 over n stays in h sub j 0 n, which is subset to O. So essentially just by cutting up this sigma into subpaths, we can add all those up, and each one of those is path independent because they stay in this tile, h sub j 0 n, which is subset to O. So we can just use these straight linear paths. Similarly, so this similarly applies for gamma. So that's that. And then we can say, moreover, if we sum up the path integrals for around the edge the path integrals between the corners of h j k n, we should also get 0. Some of the path integrals between the corners . So the way we're going to express that is we'll say, let's see, so we have the integral from some point to some other point, fx dx, and then we'll add up all the other ones. So the points that they will be is actually f of something. Oh yeah, let's actually do that up here. So we're going to replace this, instead of doing sigma, we'll do f. So we'll do f of g over n 0, f of g plus 1 over n 0, sigma t equals f t 0. So how is this going to be? So this will be, we want this to be in counterclockwise direction. Okay, so if we start on the lower left corner, which will be j over n, k over n, then we'll advance to the lower right corner, which is by adding 1 to j, and then we will add 1 from j plus 1 to k plus 1. I don't know if this is all going to fit. It's also going to look terrible. K plus 1 to n, down j, and then finally back down k. I think that is maybe correct. That is terrible. Let's label these integrals, because that's really awful. Let's see. I actually had a nice labeling scheme for this in my previous proof, in my first draft. So I think we're going to borrow that. Maybe. I0 and I1. That seems like a nice... Okay. So let's say blah 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 blah. More limits than actual integral? Yeah, it's very not good. So for convenience, so we'll do I sub 0 jk will be this integral from, we'll do fjk to f j plus 1k, and actually these should be over n. J over n, k over n, and j plus 1 over n to k over n. And we're also going to have I1. And of course this is fx dx. Okay. For jk in 0 to n, because we want the edges as well. Okay, so that's that. So since we have let's say by the previous theorem and the fact that each f of h jkn is subset equal to O sub jk, which is convex. So, blah is convex. The integral of f around the edge of any h jk tile vanishes. So we'll express that as I0 of jk plus I1 of j plus 1k plus minus I0 of j plus 1 k plus 1 and minus I1 j plus j k plus 1. Okay, so this is just taking the integral around the edge of these HJK tiles. This will be 0. We also have likewise we have since the integrals are path independent, the integral of f over either sigma or gamma can be expressed as a sum of I0 integrals as follows. And so that'll be the integral on sigma f of x dx. So this is what we were trying to do before. So we have the sum j equals 0 up to n minus 1. And we do I0 j0. And we also have the integral on gamma is the same thing that we just used n here. That should be correct. Let's also give these some more space. So the integral around the edge of these tiles vanishes. Since the integrals are path independent, the integral of f over either gamma or sigma can be expressed as a sum of I0 integrals. So essentially these I0 integrals, this is actually just a polygonal path. So we're saying approximate sigma with this polygonal path. Since it's path independent, these should actually be identical. So for each, we break up sigma into these subsections, and then we just use these direct paths, I0. And this one should be gamma, not sigma, the second one. So this is enough, actually. I think this should be enough. Almost. Since we have f of, we have t, oh, let me think. It's the vertical s. Since f0s and f1s are constant with s, it follows that the vertical integrals there are 0. So we have I1 any j with 0 is 0, and also I1 of any j, sorry, not any j, any k with 0, or any k with n minus 1. Sorry, no n, just n. Okay, so I think we don't need this other stuff. Give me some space there. Okay, so I think now we just need to add the tiles. So we've got, so if we go around one of these tiny squares, it's 0. If we go around the path sigma, it's fine enough to just go around these polygonal approximations. This is valid since each one of these polygonal approximations is sort of in these small OJK convex sets, and that's where sigma is staying in. So we should say okay. So now we just want to do it. Okay, so integral of sigma of f of x dx. This is the sum j equals 0 to n minus 1 I 0 j comma 0. But we know also let's see here. I think what we want to do is just add up all of these integrals, just all of these for every jk. So we can actually just say, take this and add the sum. We'll do j equals 0 to n minus 1, and the sum of k equals 0 to n minus 1. We'll just do all of these 0 terms. So all of these terms are 0, and we're just going to add them all up. And that does not fit. That's funny. Okay, let's do this another way. We'll do it this way. Okay, yeah. So we're gonna, we'll add up all these. So each one of these is 0. That's not right. That shouldn't be there. Let's get that out of there. Right, so we add up all these 0 integrals. Why is it still there? What the heck? There we go. Okay, so all of these are 0, so we just add them up. But these should telescope. So as we change the value of k, so we're running through k, we have I0 jk. Yeah, okay, so we can just do a little index shift. So what we want to do is we want to say this is essentially all of these cancel out. So we have let's see, let's separate these up. So we'll do this all sum on this. So we have jk, and then we'll also have I0. We'll subtract this all sum of j plus 1 k plus 1, but we can also do an index shift, so we can do this j equals 1 to n, k equals 1 to n of jk, and we can also add again this summation of these, and then we subtract the same summation of these other ones. Let's see how that looks. Really bad. Okay, that's not terrible. So we distribute all those things. Let's do an index shift on these other terms. So on this k1, instead of going k from 1 to n, we're adding... Oh, because I already did the index shift. Oopsie daisy. This should be like that, I think. Okay, I think that's correct. So we have these expression, same bounds. We have this expression, which should be, actually we'll put these in the order that they appear in, so that it's super clear. Right, so we have this expression, same bounds, but we have j moved up by 1. And actually this shouldn't be j plus 1 anymore in that case. It should be just j. Then we have this I0. We're subtracting these I0s. We have j plus 1, k plus 1, so we have index shift both of these up. And then we're subtracting I1. We have j, k plus 1. And then we just shift the k up by 1. This lets us cancel all these out, now that they're all aligned up. So this should be, rearrange these sums so that they are next to each other. So we have the summation k from 1 to n, j from 1 to n, and oh, that's interesting. I think that should be not correct. Let me think about that. That's correct. It shouldn't be that way. Let me look at this. So this should be jk to the right, j plus 1 k to the 1 to the right, to the up direction, which is 1. And then this should not be j plus 1 k plus 1 to the right. It should actually be j plus 1 k plus 1 to the left, which is negative of this coordinate, actually, j k plus 1. So this should be that, and this one should also be this. think. That seems correct. I'm gonna have to fix that. Okay, so we've got this. And we're gonna plug that in right down here. So we have these summations. And we'll do this. And we'll do the same thing, but I'll just do it correctly this time. So we have these summations, and we're just gonna split these up. So we have I0, add up this I1 term, subtract off this I0 term, and then subtract off this I1 term, and then we're going to do our index shifts. So we have this j plus 1, so j gets incremented by 1. And over here we have k plus 1, so this k gets incremented by 1. That is correct. And this makes it a lot easier. This makes a lot more sense. This is what it's supposed to be. Let me just put these like terms next to each other. Here we have j0 on each expression, and we just want to get rid of that is I1. That doesn't belong there. It should be this one. There we go. And so we'll just have the lowest term of this, so when k is 0, and we'll subtract, so all the other ones cancel out, and we'll be subtracting the term when k is n. And over here on this other one, we can just flip-flop these k sums. So these will be the same. And we will cancel these out. So this one goes j from 1 to n as being positive. So this one will get the j being n, and this other one will get j being 0. We'll put these in parentheses. Okay, that seems good. So then the sum of I0 terms with j0, and the sum with jn, this is just the sigma integral minus the gamma integral. Yes. Is that right? Let's see. I feel like it should be the other way around. Let's see, I0, JK. Oh no, this is correct. Yes, this is correct. Okay. Cool. So we just sum up all these terms. All of these are 0, actually. So then this just ends up being integral on sigma f of x dx minus the integral on gamma f of x dx. And we're done. That is the proof. Awesome. Yes, so this is a lot shorter than I thought it would be, which is pretty nice. So that is the proof. So we can sort of go back over this. So the proof, the theorem, is to show that if we have a locally convex set and a differentiable function, then two homotopic contours in S have the same integral. And so we're saying, so the proof follows since we have these homotopic functions, we have this homotopy f, capital F, with these boundary conditions. So s is 0, we get sigma, s is 1, we get gamma, and if we're on the boundary, if t is 0, we get this endpoint, and if the first endpoint, and if t is 1, we get the second endpoint, regardless of s and t, or sorry, regardless of s. So we just sort of let U be the set of all relatively open convex subsets of S. S is locally convex, so use an open cover. What we do is we cut up we want to cut up our square for our homotopy F small enough so that all of these sort of paths are within one single convex set in O and U. So for convenience, we say for each one of these n's, let H be the subtile, and we're supposing by contradiction that we can't find a large enough n to cover all these tiles with convex open sets. So that follows that there is, for every n, there's some j and k, such that no open set has F subset this image, the image of this tile, this jk tile, subset to O. But each of these corner points are in 0, 1, which is sequentially compact, 0, 1 square. So we have this convergent subsequence. S is locally convex, so we find this open set O and U with this limit point f of st in this open set. And then we just say, well, by premise, none of these tiles could be covered by O, so we just find some xm and ym, which is not in this open set O under F. This has to have this limit point going to s and t, and f is continuous, so f of xy tends to f of st, which is in this open set. Since it's open, eventually these points have to be in the open set O, which is a contradiction of the premise. So from the above, using that contradiction, we find n such that for all jk, we have this open set O with this tile. Actually, this should be f, the image of this tile. The image of this tile is subset to O, and this is going to let us use path independence for convex sets. So for convenience, we just, for each of these j and k, we label these integrals. So these are, these I0 are horizontal integrals, and the I1 are vertical integrals. So I0 is going in the j direction for our domain of f. So the value that's changing is this path along j. And I1 is going in the vertical direction, so the value that's changing is the second coordinate. So by this previous theorem, in the fact that each of these tiles, the images of these tiles are under subset to these convex sets, the integral of f around the edges of these tiles vanishes, and that can also be expressed as this sum of integrals. So all of these will vanish. Similarly, if we cut up these paths sigma and gamma, using the path independence, the integral of f over either gamma or sigma can be expressed as these I0 integrals, which is like these. Just these sum up all these components. And then finally, since we have f of 0 and f of 1 are constants with s, these vertical integrals on the edge are 0. So we have these. And then we just add up all the tiles. So we know each one of these is 0. So if we add up all of them, they're still 0. So we just add up all these integrals along all these tiles. And then we just rearrange the sum to end up in this position. These ones were 0 by observation here, and these ones are just sigma minus gamma by observation up here. And that's we just get 0 equals this difference of integrals, and we're done. So that's nice. So any two homotopic curves have the same integral for a differentiable function on a locally convex domain. We can add a corollary. So let S subset to A be locally convex and simply connected and F map s to a differentiable, then the integral of f on any loop vanishes. Oops, that's not all right. There we go. So the proof for this is just kind of straightforward. So we can just say since S is simply connected, any loop is homotopic to a constant function, a constant path. Which is a contour with 0 length. So it's the integral is 0. And it's just kind of a one-line, two-line proof. Pretty straightforward. So S is simply connected, any loop is homotopic to a constant path, and constant paths are contours with 0 length. So the integral is 0. So pretty straightforward, pretty nice. That's very neat. It's actually so nice. I almost don't want to write more because I'll just make it worse. Okay, so this is most of what we want to get through, actually. I think we can probably get into analyticity now. I think we have enough. I think we do have enough. Okay, yeah, so we can try to start on analyticity. We can only start the section off, and we'll figure out what we want to do from there. Things are going pretty well, though. I'm quite pleased. So we'll go here. Oh, let's do some examples in the power series section. Let's do the geometric series, actually. This one's really easy. See, so f is differentiable and this, and then we have can just add a note here. Actually, no, I won't. Let's go down. Yeah, we'll just do an example here. Hold on. That's not what I wanted. Okay. for any x in, let's say, a star with p1 of x minus 1 less than 1, okay, and I think that should be, I think it's 1 minus x, the power of n. That seems correct. Yeah. So for any x in A star with x close enough to 1 on the first projection, less than 1, the x inverse, this multiplicative inverse, is just given by this geometric series. So the way we do that, so we have So it's pretty much the exact same proof as usual. So the only thing we need to note for this geometric series is that it converges, and once it converges, the proof for what it is, given continuity of product and sum, is exactly the same. So if we take this and we multiply it by 1 minus x, this is just the same summation from 1, which in turn is the summation from 0, but we just subtract 1. Yeah, that's fine. I don't really want to do more than that, I guess. Just have a nice little geometric series. We will use this, but it's nice to just sort of have this example. I don't even really want to call it a theorem, to be honest. We could try something else, though. We could be a bit more general, if we wanted. like for example, we just put a constant here. And this would be no, this is fine. I'll just leave it like this. Okay. So analyticity. So what do we want to do here? So I guess we'll present the definition for analyticity. So function f mapping s to a is said to be analytic when let's see. Let's try to follow convention, actually. That's not what I wanted. I want to check if they exclude isolated points on the domain. Locally given by a convergent power series. Okay, well that's not helpful. Type are infinitely differentiable, blah blah blah. Real analytic on an open set if we can write this power series. So they're saying an open set. Well, I don't want to do that. A real analytic function is infinitely differentiable such that the Taylor series at any point x0 in its domain converges to the function in a neighborhood pointwise. Okay, that seems more explicit. Infinitely differentiable such that the Taylor series converges. Okay, so we'll say then it is infinitely differentiable and infinitely differentiable at every point, and we can say infinitely differentiable and these Taylor series is centered at any point converges in the neighborhood. We can say equivalently f is analytic when S has no isolated points and there is a for each point x0 in S, there is a power series centered at x0 and converging to F in a neighborhood of x0. So both of these definitions are equivalent. So right now, as of now, we don't know that there are any analytic functions. Actually, we can probably be pretty confident that polynomials are analytic functions. But other than that, we don't really know about anything. We do know that power series themselves have a power series expansion, but we don't know if they are analytic. We don't know if they have a power series expansion at every point. What we're going to do, so through this section, we're going to consider a very limited sort of domain. So actually, we can start off with a proof right away if we would like. Because this proof doesn't require too many things. So we can say Okay, so let's say so let's do a theorem here. So our theorem is let S be subset to A be connected and FG analytic on S. Actually, we can say, let's compact this a little bit more, on a connected domain. Connected domain S subset to A, and such that we want to say the set So the identity theorem is this statement. So let f and g be analytic on a connected domain S subset to A, and such that this set, the set of x in S, such that f of x equals g of x. We can say this set, and such this set is admits a limit point. Then f and g are identical on S. And so the proof for this, you use of course, a connectedness argument. So we'll say, for convenience, let E be equal to the set of x in S such that f of x equals g of x, and by premise, the set of accumulation points E prime. So we're going to say, yeah, the set of limit points E prime subset to E is not empty. I think this is fine. Okay, yes. So it's not empty. We'll show that E, actually we can just do this. We don't even have to say it. So since, actually we can say, let me think. Let E sub infinity be the set of x in S such that for all n, f, we have the nth derivative at this x is the nth derivative of x. Yes, okay. So we're saying E is the set where f and g are identical. By premise, the set of limit points E prime subset to E is not empty. actually this isn't subset to E, we can say subset to S. Is non-empty. Let E sub infinity be this set. So this is be the set where the Taylor series for F and G are identical. So clearly we have E infinity subset equal to E. Actually, we can just say, let's be a little bit more clear. I think we don't need any of these sets. So we can just say, let E be the set where F and G have the set where the Taylor series of F and G are identical. Okay, so oh gosh, maybe I guess we do need them. Okay. Okay. For premise, the set of accumulation points E prime subset to S is non-empty. Actually, we can say, since both F, G are continuous, then E prime, we can say, the set of accumulation points E prime subset to E is non-empty. Oh gosh. And since both F and G are continuous, E prime is subset to E. Okay. So we want to show that E, the set E, where F and G are identical, is both relatively open and closed. So okay. So we can say, since FG are analytic, we have their series converge in an open set, and thus actually we can say the derivatives of well, let me think. Okay. I think what we want to do first is since the derivatives are recoverable from a limit point, we should have the set of limit points for E, the set where they agree, is actually a subset to E sub infinity. So explicitly we would have let's say let x0 be in E prime, then consider we have f of x, actually we're going to say for x close to x0, f of x is the sum, n equals 0 to infinity. We have f nth derivative at x0 over n factorial, and we also have oh, maybe we could be a little clearer. I think we can actually, instead of considering two functions, we can just consider one function. Instead of considering the set of points where they're equal, we can consider the set of points where they're 0. So f is analytic on this domain is such that the set x such that f is 0, emits element point, then f is identically 0 on S. That'll make it a little easier. We can add the full version as a corollary. So we can say, let's use the set of f, set where f is 0. And E z infinity is the set where every derivative of f is 0. Let's think here. Actually, yes, this works a lot better. Okay, so so what we're doing now is we're saying z is the set where all the derivatives of f are 0. Since the derivatives are continuous, z is a closed set. So we could think of that as a continuous preimage of the closed set 0, which is closed. Preimage of a closed set is closed. So the set where all the derivatives are 0 is closed. It's also going to be open. So in particular, let x0 be in C, then there is a neighborhood O over which x in O have this Taylor series. So f of x is the sum n equals 0, infinity, and we have this fraction f nth derivative at x, 0 over n factorial. And this is x minus x 0 to the power n, but this is just the summation of all these zeros. All these derivatives are 0, which is just 0. So we have this O is actually we can say by taking any mth derivative, similarly we have, so if you take an nth derivative, we have this summation, this will be, that'll stay as it is, and then we get n minus m, and then we have, oh gosh, how does that work out? We had a formula for this, for repeated derivatives. I don't want to do it again. I think it was this one, right here. M factorial over n minus m factorial. This will be from n equals m, and this will be, so, and we just need to swap n and m. N factorial over n minus m factorial, I think. Okay. And we still just have a bunch of zeros. Okay, so Z is a closed set since all the derivatives are continuous. Z is also an open set since we can calculate all the derivatives from a power series. From the Taylor series, which is just going to conversion in an open set. And then finally we have, let's be a bit more specific. So since S is connected and Z is both open and closed, either Z is S or Z is empty set. However, by premise, we have some limit point for fxn equals 0. So let's say x of n be a sequence, and a natural in S be a convergent sequence with limit x sub n going to x, doesn't matter. Actually, we'll just call it x0. And then we can say so again, by continuity, we have f of x0 being 0. Actually, we can just do this all in one step. So by induction, let n in n0 be the least, actually, takes on n and n0 such that all n less than n have f nth derivative at x0 being 0. Which is vacuously true when capital N is 0. Then we have f of x of n is this. Actually, let's use a different indexing. X of n, that'll be a little better. Okay. X of m, this will be we take this power series x0, so sum, and so we'll start from capital N, this derivative, and then we have x minus x0 power n. But then we can also say, if we just take is f, we can do a fraction f of xm, we'll subtract f of x0, and then we'll divide by x minus x0 power n plus 1. Power n, capital N. And this will just be, actually it's fine if we just do it like this. This is the summation. We're doing little n up to subtract capital N. We should have a new line here. And we can do x minus n0 power n. This should be this same summation. And we can do an index shift now. Instead of n being capital N, we can go n from 0 and just add capital N at each of these points okay, so we've got fx sub n, fx sub m is this summation. This should be x sub m in here, as well as in there, and there. Okay, so we'll do it like this. We'll do actually the derivative. Okay. So the nth derivative at x sub m is this summation. We have sum n equals n to infinity, fn x0, n factorial, blah blah blah, which is this. Okay, and then we'll do this index shift to make it clear what's happening. So n from capital N will go from 0, add n to all of these terms. And actually these factorials will cancel out, and we should get rid of them. So we have 1 in this numerator, 1 in this denominator, and then we just end up with n factorial down there. And then we can say limit as m goes to infinity. We say actually f nth derivative at x0 is equal to this limit of f nth derivative at xm, and this is just this doesn't help me at all. Wait, yes it does. No it doesn't. This doesn't help me at all. Gosh dang it, I should have done what I was doing before. Hold on. Okay, let me look at this for a second. xm is the summation. This should be x of m. And then we have this other term. If we pull out, this is fine. And then we're just trying to factor out the whole expression. Plus n, and then we just have capital N. Okay, there we go. Okay, now we have f nth derivative at x0, and we can actually say nth derivative at x0 over little n plus big N factorial is just equal to this limit as m goes to infinity of this power series, which is actually just this limit of the fraction f of xm over x minus x0 xm minus x0 to the power of n, which is 0. Okay, there we go. That's what I wanted to do. Okay. So just to check again, xm is the summation, factor out these terms, fn power x0, or f nth derivative at x0. Let's make sure I put parentheses there. The nth derivative at x0 divided by n plus n factorial is this limit as this thing as m goes to infinity. Actually, we can also say the limit as x goes to x0. That's not there. Okay, and that's it. Okay. And let me just make the alignment a little better. Okay, so we've got all these derivatives working out. And so we can also multiply by n plus. No, this is fine. So it follows by induction. This shouldn't be lowercase n. This should just be capital N factorial. So it follows by induction that for all n, we must have f n at x0 being 0, and thus x0 is in the Z set. So Z is non-empty, and therefore Z equals S by connectedness. Okay, so to summarize this proof, we're saying if f is analytic on a connected domain, and the set where f is 0 has a limit point, then f is identically 0 on S. So the set of points where f is equal to 0 is actually all of S. So the proof, so we take Z to be the set where all of the derivatives of f are 0. Since the derivatives are continuous, Z has to be a closed set. So if we have, some sequence in this set where all these derivatives are 0, limiting to a point, that point also has to be, all the derivatives are continuous, so that point also has to be in Z. Also, since f is analytic, Z is an open set, so essentially each Taylor series converges in a neighborhood of the point. If all the derivatives are 0, the Taylor series converges to 0, so the function is 0 in a neighborhood of a point. Or by taking the mth derivative, all the derivatives are 0. So there is some neighborhood, the neighborhood where this power series converges, which is subset to Z, so Z is an open set. Yes, and then since S is connected and Z is both open and closed, either S is Z or Z is open, or Z is empty. So either it's empty, it's nothing, or it's all of it. So that's the connectedness argument. And by premise, we have some limit point for f of x equaling 0. So there is some limit point for this set. So we can find the sequence x of m with this limit xm going to 0. We can say, so let these be convergent sequence limit this, and having fxm be 0, be precise about that. So we have the sequence on which f is 0, which has the limit point to x naught. By induction, we're just going to say, inductively, suppose we have some n such that all of these lower indices have this nth derivative 0. This is vacuously true when capital N is 0. And for all sufficiently large m, we just calculate f sub m, f of x sub m using this Taylor series. So this Taylor series we just use the standard Taylor series. All these lower derivatives are 0, so we can just factor out this power, x power capital N. If we divide by this x power capital N, that'll be f of x sub m will be divided by this, and that will just give us, that will be equal to this Taylor series, this power series. But if we limit m to infinity right here, this Taylor series just limits to its first term, its first non-zero term, its first non-constant term, or sorry, its first constant term, x power f which is when n is 0. So we take this, divide it by this, that gives us this fraction being equal to this summation, which is this one here. And if we just limit this x goes to x0 of this expression, this whole expression just limits to its first term, which is this derivative. So by induction, so we've proven if we have all of these lower indices having 0 derivatives, then this capital N also has a 0 derivative, the nth, capital Nth derivative. So by induction, that follows for all of these n's. And so we have to have all of these derivatives being 0. And since all the derivatives are 0 at x0, then x0 is in the set z. So z is non-empty, so z has to be s, since we've since it's open and closed and non-empty, and s is connected. And that's essentially that proof. This is really useful. This identity theorem. We can add sort of a corollary as for, if two functions are equivalent on a limit point. It essentially just allows us to say if we have a connected set, then functions are very unique, in a sense, analytic functions. What we want to do next time, when we get to this, what we want to do for our next proofs is we're actually going to prove that if we have a special type of domain, that every differentiable function is analytic, in fact. It will have to be a special type of domain, though. In fact, it relies on the same principles from complex analysis. In fact, the proof is pretty much the same. But we'll end up finding out that differentiable functions, so long as we have a really nice domain, differentiable functions just end up being analytic every time. However, I think we've gone on for long enough today. So I'm going to stop us here and cut us a little short. Usually we go for longer. But I'll say that's what we'll do. That's all we'll do for today. Do you have any questions on any of this so far? On this identity theorem, or the other proofs we had done on integration? For path independence, and so on. Not I. Okay. Not imaginary. That means you have a real question. I'm kidding. It was a joke. It was really funny. I know. Okay. Great. Awesome. More writing is needed. Yeah. As always, it's the same link. You can always read this. You can also always ask me questions whenever you want. We can try some examples eventually. So one of the examples we did this, down here. We just sort of did the geometric series example. We didn't really need to. It's kind of simple, almost trivial. As soon as you know that the convergence, that it converges. And so remember, the capital phi function is just the retest. So, okay. That is okay. Then I will stop us here, and we will continue again later, at a future date. Thanks for watching and joining us on this adventure today. Goodbye.